Hello everyone, welcome to the presentation. This is Sai Krishna Sirgadi, and today my topic is about getting of metals by voids in silicon devices. So it's a, it's a topic from semiconductors. So now let's get into it. It is known that interstitial iron concentration in silicon is reduced after annealing silicon excuse wafers coated with plasma enhanced chemical vapor deposited PECVD silicon nitride films. The underlying mechanism for the significant iron reduction has remained unclear and is investigated in this work. Secondary ion mass spectrometry depth profiling of iron is performed on anneal iron contaminated single crystalline silicon wafers passivated with PECVD silicon nitride films. SIMS measure reveals a high concentration of iron uniformly distributed in the annealed silicon nitride films. This accumulation of iron in the silicon nitride films matches the interstitial iron loss in the silicon bulk. This finding conclusively shows that the interstitial iron is gathered by the silicon nitride films during the annealing over a wide temperature range from 250 degrees centigrade to 900 degrees centigrade via segregation Gettering effect. Further experimental evidence is presented to support this finding. Deep level transient spectroscopy analysis shows that no new electrically active defects are formed in the silicon are formed in this silicon bulk after annealing iron containing silicon with silicon nitride films, confirming that the interstitial iron loss is not due to a change in the chemical structure of iron related defects in the silicon bulk. In addition, once the annealed silicon nitride films are removed, subsequent high temperature processes do not reach in any reappearance of iron. Finally, the experimentally measured iron decay kinetics are shown to agree with a model of iron diffusion to the surface Gettering sites, indicating a diffusion limited iron Gettering process for temperature below 700 degrees centigrade. The Gettering process is found to become reaction limited at higher temperatures. So now let's go into the introduction. Here we are talking about the Gettering of interstitial iron in silicon. So actually our topic is about getting of metals by voids in silicon devices. Iron is a metal. Now we are getting an example here. Introduction. Iron is a harmful and common metallic impurity in the silicon materials used for solar cells and microelectronics. In the solar cell fabrication process, the detrimental impact of the iron is commonly mitigated by the gathering of iron to the heavily phosphorus doped regions near the wafer surfaces during the high temperature phosphorus diffusion process used for the PN junction formation. Heavy boron diffusion heavy boron diffusion or aluminum alloying process could also achieve similar gathering effects. If well integrated into the solar cell fabrication processes in, in a place called Glokalski silicon for microelectronics, the gathering of dissolved iron is commonly achieved by driving iron precipitation at intentionally introduced oxide precipitates in the silicon bulk via low temperature annealing similarity in multi-crystalline silicon materials for solar cells. The overall impact of iron can be elevated by driving iron precipitation at the crystallographic defects. Although the process is much less effective than the higher temperature phosphorus diffusion getting approach. Numerous studies have shown that the annealing silicon wafers with plasma enhanced chemical vapor deposited silicon nitride films at high firing temperatures cause the concentration of dissolved iron, that is interstitial iron, in silicon to be reduced significantly. The mechanism for this iron reduce has remained unsolved, and it has been hypothesized that it might be caused by the hydrogenation of iron in silicon. This hypothesis was based on the reports thus shown The recombination activity and the concentration of interstitial iron in silicon were reduced after hydrogen incorporation via exposure to hydrogen plasma. Hydrogen ion implantation, wet chemical etching, or deposition of PECVD silicon nitride films. While there have been reports of the detection of new defect levels assigned to the possible FEH complexes, from the theoretical calculations, the binding energy of FEH pairs was radical calculations, the binding were found to be weak, indicating the unlikelihood of the FEH pairs withstanding the relatively high temperatures used for firing. Others have suggested that the reduction was due to the accelerated precipitation of iron driven by hydrogenated enhanced iron diffusivity. However, this hypothesis cannot explain the observation iron at higher annealing temperatures, at which the iron solubility limits were well above the iron relaxation precipitation process should not proceed. This work aims at uncovering the underlying mechanism responsible for significant reduction of the interstitial iron concentration in silicon after annealing with PECVD SiNX concentration films. Secondary iron mass spectrometry analysis of the depth profile of iron was used to examine the distribution of iron in the annealed NX films and Si wafer substrate. Deep level transient spectroscopy was applied to the annealed silicon samples to determine whether any new defects with deep levels were formed. The SiNX coated annealed samples were also subjected to further high temperatures processes to monitor any changes in the interstitial iron concentrations. Finally, the experimentally measured iron decay kinetics at 250 to 900 degrees centigrade were analyzed using an iron diffusion model, and the fitted apparent diffusivities compared to the reported iron diffusivities in the literature. Now let's go to the experiment 2. A flowchart outlining the experimental procedures is shown in figure 1. This is the figure 1, and in this figure we can see the different samples preparation is given. So now let's read about it. Boron doped p-type float zone silicon wafers were used in the work. The samples in experiment A, C, and D had a resistivity of 1.7 ohm centimeter and a thickness of 250 mu meters after chemical etching. The samples in experiment B had a resistivity of 8 ohm centimeters and a thickness of 500 mu meters after etching. Prior to iron implantation, the samples were chemically etched in an alkaline solution to remove saw damage and were subsequently RCA clean. Iron implantation was carried out using relatively low implantation energy of 7 kilo electron volts with a beam current of around 50 nanoampere scanned across a 3 cm cross 3 cm aperture. These implanted doses of iron were 5 cross 10 power 11 per centimeter square for the 500 millimeter thickness thick wafers and were varied from these parameters for the 250 millimeter thick wafers. The samples were then annealed and distributed implanted iron throughout the wafer thickness. The solubility limit of iron in silicon is 1000 degrees centigrade is 4 into 10 power 14 per centimeter cube, well above the target volumetric interstitial iron concentrations of 2 to 10 power 12 to 10 power 13 centimeter per centimeter cube. Dry oxygen was used as an ambient gas for the anneal in order to facilitate the growth of silicon dioxide layers of around 100 nanometer thick on the wafer surfaces, which not only acted as the diffusion barriers for any possible furnace contaminations but also provided sufficient surface passivation for samples that were set aside silicon oxide and controls samples that were set aside cool down from 1000 degrees centigrade to 750 degrees centigrade at a rate of 10 centigrade per minute. Before being removed from the furnace and cooled in a high airflow to reach room temperature in minutes. A subset of the samples had the SiO2 layers removed in the dilute HF solution and then received a shallow chemical etch in HNO3 HF solution to be remove any possible implantation damages near the surfaces before being coated with PECVD silicon nitride films on both sides. The silicon nitride films were deposited using an AK-400 microwave or radio frequency PCVD reactor manufactured by Roth and Rowe. The films were deposited at a substrate temperature of around 250 degrees centigrade under a pressure of zero point 0.2 millibar, a microwatt plasma power of 500 watts, and a RF bias voltage respectively. The deposition was three times the deposition time was 3 minutes. The resulting film thickness was 90 plus or minus 20 nanometer with a refractive index of 1.93 at a wavelength of 632 nanometers. A hydrogen content of given parameters and a silicon nitrogen bond density of equivalent to 9 into 10 power 22 per centimeter cube. Note that the deposited SiNX films were optimized for the surface passivation and anti-reflection purposes, not for the most effective removal of iron from the silicon bulk. A quasi-steady state photoconductance lifetime tester from Certon Instruments was used to measure the bulk minority carrier lifetime, and the interstitial iron concentrations were determined from the carrier lifetimes in the isolated iron and ferroboron paired states. Strong illumination was used to dissociate the ferroboron pairs. Here he has given a flowchart, we can see it thoroughly. Next, the reported error bars in the measured interstitial iron concentration resulted from assuming a 10% uncertainty in the QSSPC lifetime measurement before and after dissociation iron boron pairs. The QSSPC lifetime technique is used throughout this work to measure the interstitial iron concentration in silicon bulk. Interstitial iron refers to the total electrically active iron in silicon which pairs with boron in the equilibrium state forming boron pairs. In experiment B, the DLTSA technique is also used to determine the iron concentration from measuring the iron boron concentration in samples kept in dark. SIMS measurements in experiment A, however, detect the total concentration of iron regardless of the electrical state. SIMS measurement of the redistribution of iron. The following samples were prepared for SIMS analysis. Here he has given 5 points which are used for redistribution of iron. This is also one method of Gettering. The wafers were removed from the furnace at the respective annealing temperature, followed by a rapid cooling down in high airflow within minutes. For the Fe implanted samples annealed by PCVD SINX films, the chosen annealing conditions were found to result in significant reduction of the interstitial Fe concentration in silicon, as will be confirmed later in SEC. To monitor the changes, one set of the samples from each of the above processing condition had the annealed SINX or SiO2 layers removed and were repassivated with PCVD SINX to enable QSSPC measurements of the bulk, lifetime, and iron. Another set of examples with the annihilated silicon nitro or silicon dioxide surface layers was sent to Evans Analytical Group EAG laboratory for SIMS depth profiling of the iron concentration in SINX or SiO2 and the SS substrate. The nominal measurement depth resolution was better than 1.5 nanometer or step, although the actual resolution was limited by the mixing of bombarded ions through SIMS measurements. The direction limits for iron were given parameters. Silicon was monitored as a marker species with its secondary ion intensity qualitatively measured, which served the distinguished locations of SINX or SiO2 and the Si bulk in the depth. DLTS analysis. Iron implanted silicon wafers with either PECVD SiNX or thermally grown SiO2 were annealed at 700 degrees for 30 minutes in nitrogen. The annealed SiNX or SiO2 were the removed dilute HF solution, followed by a repassivation using PECVD SiNX to allow QSSPC measurements of the bulk lifetime and FEI. After measurements, the SiNX films were removed in dilute HF. The samples were then chemically cleaned and etched again to remove about 45 micrometer from each surface in order to probe the bulk defect concentration using DLTS. The efforts were subjected to a 1 minute dip in dilute HF before the deposition of Scotty barrier diodes. The Scotty diodes of 1 millimeter diameter were formed on the p-type samples by plasma sputtering of titanium through a shadow mask. A layer of forum was evaporated on the backside to form an ohmic contact. Current voltage and capacitive voltage measurements at the different temperature were carried out in order to check the quality of the diodes and to determine the concentration of non-compensated shallow acceptors or donors. Deep electronic levels were characterized with conventional deep level transient spectroscopy DLTS, Laplace DLTS, and the minority carrier transient spectroscopy techniques. For the MCTS measurements, a flux of minority carriers for recharging traps in the upper half of the SI band gap was induced by backside light pulses from a 940 nanometer light emitting diode. Post Gettering analysis. Iron implanted silicon wafers in the range with PECVD SNX were annealed at 700 degrees for 30 minutes in nitrogen to reduce the interstitial iron concentrations. The annealed SNX films were stripped of dilute HF and the samples were repassed with SNX so that accurate QSS measurements of the silicon bulk were possible. The SNX films were then stripped off after QSSPC measurements and then sample received a shallow chemical etch to remove any residual nitride films. Additional samples were included which did not receive any surface etching after receiving the SNX films in dilute HF. So now let's go to the results. The initial interstitial iron concentrations in the FZSI silicon wafers resulted from Fe ion implantation and the subsequent distribution anneal were found to be in the range of 2 into 10 power 12 to 10 power 13 per centimeter cube from QSSPC lifetime measurements. The measured interstitial Fe concentrations agreed well with the implanted Fe dose. So this is our topic, and here few graphs are given based on this and their changes and their observations. Okay, and let's go to the conclusion part now. The dis- The disappearance of interstitial iron in silicon after annealing silicon wafers with PCVD silicon nitride films is found to be due to the segregation Gettering of iron by the SiNX as evidenced by SIMS depth profiling of the Fe concentration as evidenced by SMS layer and the SI substrate. A high and uniformly distributed concentration of iron is measured in the annealed SiNX films, and the iron concentrations from quantitative SIMS measurements match the losses of interstitial iron. From the silicon bulk measured by QSSPC to the finding that the interstitial iron in the SI bulk can be effectively removed by the PECVD SNX films at elevated temperature via segregating getting effect is further supported by the following experimental results. First one, the DLTS analysis revealed no new defect levels in the silicon band gap after annealing with SNX. Second point, post-Gettering anneals of the SiNX tripled silicon samples do not result in an appearance of iron. Third point, the measurement iron decay kinetics at 250 to 700 degrees centigrade are consistent with a model of diffusion limited Gettering of iron to the wafer surfaces. The segregation Gettering process is found to occur in a wide temperature range, and the process becomes reaction limited rather than diffusion limited at higher temperatures, 800 to 900 degrees centigrade. So this is our topic: getting of voids in silicon metals. Getting of metals in, as voids in silicon. Thank you.